Okay, so I want to talk about a really important application of Bayes' rule and conditional probability to the problem of medical testing. So this is something that's obviously on everyone's minds with COVID, but certainly it's an issue all the way going back to taking biopsies of tissue for things like cancer diagnosis. So let's do this kind of worked example of medical testing. So suppose we have a test for an underlying condition or disease D. Okay, so the test manufacturer has to provide some sort of statistics about how well this test performs. So suppose that this is what we came back with. The probability that the test is positive, given that the patient has the disease, is 0.99, right? So that's great, right? That means that if you have the disease, the test is very likely to show up as positive. But there are always, some possibilities that you have the disease, but the test comes back negative, right? So that means that what's left over is 0.01. Now this is called a false negative, right? And certainly in the real world, this is bad, right? You don't want to go have a test and it tells you you're negative and then it turns out you're later positive, right? So this number should definitely be small and this number should definitely be big, right? Kind of the other statistics are we have the probability of a positive test given that you don't have the disease, which I'm going to, make this little tilde to mean no disease, right? So this number we want to be small. Let's suppose that for this test it's 0.05, right? That's what's called a false positive. You're healthy, but the test comes back and says that you're not healthy, right? So, both false negatives and false positives are bad. You can argue about which one is worse. Arguably, false negative is worse because then you go on thinking that you're healthy, but you're not, whereas a false positive maybe just means that you have to quarantine for 2 weeks and everything was fine, right? So, regardless, both these things should be small. And then, to finish it out, we want the probability of the test being negative when you don't have the disease also to be large, right? So this kind of stands to reason for how we want a test to behave. And let's also suppose that we know from looking at all the people that come into hospitals that the probability of the disease is pretty small, right? This is not widespread. It's a rare disease. 1 out of 1,000 people has this disease, okay? So now we do a test and we want to find out what's the probability the patient has the disease given that the test was positive, right? That's a very natural thing to ask. So probability of disease given that the test is positive. Okay, so we're going to use Bayes' rule to answer this question, right? We can turn it around and say it's the probability of test being positive given the disease times the probability of disease over the probability of test being positive. And furthermore, we can take this bottom part. I'm just going to write the top again. The bottom part is actually from the law of total probability. I can say, well, there's 2 ways the test can be positive. Either I have the disease or I don't have the disease. Okay, so we have all this information from the previous slide, right? The probability the test was positive given that I have a disease is high. The incidence of the disease is low. And then these 2 numbers are repeated down here. What's the probability the test is positive when I don't have the disease? Well, it's pretty small, 0.05. And the probability of not having the disease is pretty high. So I multiply all these numbers together, and you can compute the answer is 0.019. Now you think about this, you say, wow, this is actually not what I expected at all, right? This is saying that the test came back positive, but the probability that I had the disease is actually like 2%. How could that be? Well, it has to do with how bad it is to have false positives and false negatives, and also keeping in mind that the disease is very rare, right? So this is kind of like saying that of all the positive tests that I got back, it's very likely that the patient doesn't have the disease. But 5% of those healthy patients are coming back with the disease being positive, and those positive tests that are false positives are overwhelming the total number of positive tests, right? So in order to make a test really effective, you have to drive down these false positives to a much, much lower rate than 5%, right? This is like way too low for a test to be effective. So to make the test effective, or to make the test useful, the false positives must be extremely low. Right? So you might have thought that 5% was an okay number, but really what I want is something like, the probability of a positive test given no disease to be something like 0.0001, right? Very, very unlikely that you'll get a positive test back if you're healthy. And in that case, you can compute the numbers again, and you'll find that the probability of disease given test positive goes up to 91%, which is more like what you would expect, right? So this is just a simple example to show why understanding the quality of different kinds of tests and as it relates to the overall healthiness of the population is so important. That's why we have to know how effective certain tests are, and we also have to keep an eye on how prevalent the disease is. Otherwise, people who don't know much about statistics could make some really bad decisions about some really bad tests. So hopefully that's a simple illustration of why probability is so important in your daily life.